Hello, everyone. It's a pleasure for us to have Jinyoung Park speaking today. She'll talk on the number of maximal independent sets in the Hamming cube. So during the talk, if you have any questions, please write them in the chat and we will either raise it to Jinyoung if it's something urgent, or we might unmute you. But throughout the talk, everyone will be muted, and at the very end, we'll have question period where you can ask your questions. Okay, Jinyoung, you can start.
Okay, thank you. Thank you very much for the invitation. Today, I'm going to talk about the number of maximal independent sets in the Hamming cube, and this is going to work with Jeff Kahn. Let me start with some Hamming cube basics. Here we use QD for the D-dimensional Hamming cube, and this is a graph whose vertices are binary strings of length v, and two vertices are adjacent if and only if they differ in exactly one coordinate. So here I put some small examples of QD. So this is Q2 and this is Q3. And QD is the regular and bipartite on E union O, where this E means the set of even vertices, where an even vertex means a vertex with even number of ones in its coordinates. And O is the set of odd vertices, okay? And this bipartition is unique. And finally, the number of vertices in QD is 2 to the D, and we'll use big N for this quantity. So in this talk, big N always means the number of vertices in QD. And on the other hand, we'll use small n for the number of vertices in general graphs, okay? And we use MIS for a maximal independent set. And should I define what a maximal independent set is? An independent set is the set of vertices which do not contain any edges inside, and a maximal independent set is an independent set which is maximal, which means once we add one more vertex to it, that is not independent anymore. It produces some edges inside. Okay. Okay, and we use MIS-G, excuse me, for the number of maximal independent sets in a graph G. Then using this definition, our main theorem says this: the number of maximal independent sets in QD is asymptotic to 2 times D times 2 to the n over 4, which was a conjecture of Ilinca and Kahn from 2013. And I know that this expression seems quite mysterious at first glance. So in this talk, I will first introduce some general context to see why this expression is a natural candidate for this QD. And then I'll give you a little flavor of our proof, okay? So first, let's see some motivating examples. This is the first example, and so I chose this example because it gives us a big picture, but I want to clarify that this example itself is not so directly related to our work. So first, Erdős, Kleitman, and Rothschild in '76 showed that almost all triangle-free graphs are bipartite. So let's say this red circle is the family of triangle-free graphs. Then this theorem says that there is typicality in this family. Namely, when we choose a member from this family, then this member is bipartite. So the fraction of non-bipartite graphs is just negligible, this small blue circle. Then how does this typicality related to asymptotic enumeration? Notice that this theorem is actually equivalent to saying that the number of triangle-free graphs is asymptotic to the number of bipartite graphs. So, and this says that, and an easy corollary of this theorem is log of the number of triangle-free n-vertex graphs is asymptotic to n squared over 4. Here, n squared over 4 is a trivial lower bound for this quantity, because we can think about this in this way. Consider a complete bipartite on n over 2, vertices. Then the number of subgraphs of this complete bipartite graph is exactly 2 to the n squared over 4, because we have here n squared over 4 edges. So this gives us a lower bound on this quantity. Okay, and this Erdos, Gleichmann, and Rothschild says that this trivial lower bound is actually the truth for this quantity. Okay, and this gives us a tiny hint for the main theorem. Our main theorem says this. It talks about number of maximal independent sets in QD. So let's say this circle is the family of maximal independent sets in QD. Then there is a subfamily of this whose size is asymptotic to this quantity. And eventually we'll show that this subgraph is almost everything. So this trivial lower bound, this trivial lower bound is actually the truth for Miss QD. That's our plan. Okay, are you okay? Okay, then let me give you another example. This example is more closely related to our work. Korshunov and Sapojenko in 1983 showed that the number of independent sets in the Hamming cube QD is asymptotic to 2 times square root of e times 2 to the n over 2. And here you see that this 2 to the n over 2 is a trivial lower bound of this quantity. Do you see why? Because QD is bipartite. So that means every time we choose a subset of in this part, then this becomes an independent set. So from this part O, we have 2 to the n over 2 independent sets. Okay, then where is this 2 come from? Because we have 2 parts, so we have 2 times 2 to the n over 2 for a lower bound of the number of independent sets in QD. Then here we have another square root of e term. So this means there are more independent sets than this construction. And it's not so hard to see because when we choose some vertices from here and some other vertices from here, so that there are no edges between them, then this becomes another independent set. And so basically what Korshunov and Sapojenko showed is this. So let's say this red circle is the family of independent sets in QD. Then we've already seen that some of the members are purely odd, which means they are entirely in this part. Okay? And also we've seen that some of the members are purely even, which means they are entirely contained in the even part. And some other independent sets are almost odd, which means, so it has some rigorous meaning, but roughly speaking, almost odd means most of the vertices are contained in this odd part, and there are a few even vertices which are far from each other. Okay, and there are some almost even vertices with the same meaning. And Korshunov and Sapojenko showed that this is almost everything. So here we see this small tiny blue dot, and this corresponds to the other maximal independent sets, which means, the other independent sets, which means independent sets which does not come from this construction. And they showed that the contribution from the other independent sets are negligible, and the size of this red part gives us this value. And this quantity is very easy to compute because the structure of independent sets in this red part is just so simple. So again, this is actually a lower bound of the number of independent sets, but by Korshunov and Sapojenko's work, we know that this lower bound is actually the truth. Okay? Then now let's take a look at the structure of this family. So here, when we look at this family, we say that actually we can kind of like split this family into 2 pieces. One piece is this above part, the top part, odd part. And another piece is here, the even part. And in this case, we say that there are 2 phases. So this family has two phases, the even phase and the odd phase. And in each phase, for example, if we look at this odd phase, some configurations are pure and some other configurations are impure. Okay, and the same for the even phase. And with these terms, we can understand this expression better. So here, it has 2, and this represents the number of phases. So we have 2 phases. And here, we have 2 to the n over 2, and this represents the contribution from the pure configurations, right? We talked about this. Then this square root of e, this corresponds to the contribution from the impure configurations. Okay, so more precisely, the contribution from the impure configurations is actually square root of e minus 1 times whatever, 2 to the n over 2. But so maybe it's more precise to say that this square root of e reflects the contribution from the impure configurations. So that means in this expression on the right-hand side, each term has its meaning. Okay, so it's quite interesting. Then let's go back to our main theorem. It says that Miss QD is 2D times 2 to the n over 4. And here 2D corresponds to the number of phases. And 2 to the n over 4 represents the contribution from the pure configurations. And that's it. So this formula says that there's no contribution, or there's just negligible contribution from the impure configurations. Okay, so this is, I mean, the pureness of this formula is quite striking for us, because we have some other asymptotic enumeration. There are some other asymptotic enumeration problems on the Hamming cube, and as far as I know, this is the only case that there are no extra terms. So this is the only case that there are no extra terms, and we'll see some examples a few slides later if we have time. Anyway, so I think at this point, maybe some of you are curious about then what are the phases of Miss QD. So we'll move on to the phases of Miss QD. But are there any questions, or is this okay to move on to the next slide? Okay.
If there are any questions, please write in the chat. I will raise them.
Okay. So then let me talk about the phases of Miss QD, and this is where the asymptotic lower bound comes from, as we discussed. Okay, so first notice that QD is the product of QD minus 1 and K2, which means we can split the Hamming cube QD into 2 half cubes. And then there is a perfect matching between the half cubes. So for example, if we draw a picture of Q3, Q3 has 2 pieces of Q2, and there is a perfect matching. Okay, then here QD is, sorry, this half cube, this is again a Hamming cube, so which means there some of the vertices are even, which are red in this picture, and some of the vertices are odd, which are black in this picture. Okay, and the 2 copies of the half cubes are isomorphic, which means, so that means for each edge in this perfect matching, the 2 ends have the same parity. So that means some of the matching edges are even, and some of the matching edges are odd. Here, even edge means the 2 ends are even. Oh, so by the way, so when I say even and odd, this is the parity with respect to the half cube. I'm sorry, in the half cube. So in the half cube, in this half cube, some of the vertices are even and odd. And in the other half cube, because the 2 copies are isomorphic, so the other end have the same parity. Okay, so we see, again, we see a perfect matching, and the half of them are even and the half of them are odd. And what we are doing now here is to collect all of the even edges or red edges and call this collection M star. Okay? And in this M star, first, this M star is an induced matching, which means there are no other edges between the vertices other than the edges in this matching. Okay, so there are no edges between the vertices. And second, the size of this induced matching M star is n over 4, because we originally had n over 2 edges, and we chose just a half of them. Okay, and this is an easy fact about the Hamming cube. So n over 4 is the maximum size of an induced matching in the Hamming cube. And moreover, what's more interesting is every maximum induced matching in the Hamming cube is gotten by this construction. Here, when I say this construction, this means we split QD into 2 pieces of the half cubes, and then we choose one parity. So this is the only way to have a maximum size of an induced matching. So this gadget is very important in our work, so we gave a special name. We call a maximum induced matching in the Hamming cube a canonical matching. And there are exactly 2 times D of them because there is D ways to decompose this Hamming cube, and there are 2 parities. So there are exactly 2 times D canonical matchings. Are we okay? A canonical matching is very important gadget in our work for the rest of the talk. So let me repeat just one more time in case you missed it. A canonical matching is a maximum size of an induced matching in the Hamming cube, and its size is n over 4. And there are 2 times D ways to get it, which is we decompose QD into 2 pieces of half cubes. Then we see a perfect matching, and we choose one parity of them. Okay? Okay, so once we have this induced matching, or once we have this canonical matching, then we construct maximal independent sets in this way. First, we choose one vertex from each edge in this M star. Then this becomes an independent set because M star is an induced matching. Then we can extend this to a maximal independent set by adding some vertices. So in this way, we have at least 2 to the n over 4 maximal independent sets because we have n over 4 edges. Okay, and here I said at least 2 to the n over 4, but we'll see that this is actually exactly 2 to the n over 4, but let me not worry about it because we are talking about a lower bound. Anyway, so from each canonical matching, we have 2 to the n over 4 maximal independent sets, but we have 2 times D canonical matchings. So it gives us 2 times D times 2 to the n over 4 as an asymptotic lower bound of Miss QD. Here I say this is asymptotic because we have some overlaps. So there are some overlaps between 2 family of maximal independent sets gotten by different canonical matchings. But this overlap is negligible, so let me not worry about it. And the main point for our main theorem is this. We want to show that all of the other maximal independent sets, here other means the maximal independent sets not gotten by this construction. The number of this is little of 2 to the n over 4. This is the main point of our work. Okay, so are we okay with this lower bound construction or phases of Miss QD? Okay. So this is a very rough proof of plan. So we'll see. So first we claim that canonical matchings are indeed phases. So our goal is to show this, and our first claim is canonical matchings are indeed phases, which means this. So this red circle is the family of maximal independent sets in QD, and we can more or less split this family into 2 times D sectors. And each sector corresponds to a canonical matching M star and a maximal independent set in this sector either looks like this, which means it hits all of the edges in M star, or looks like this, which means it hits most of the edges in M star, but it misses a few edges. okay? And so we claim that the number of maximal independent sets which are not in this phase, in these phases, is negligible. Okay, one more time. Claim 1 says that typically when we choose a member of this family, then there is a canonical matching M star so that this maximal independent set hits all of the edges in M star, or it hits most of the edges in M star. That's the meaning of the claim 1. And once we show this claim 1, then we can focus on one fixed phase. So we show that in each phase, first, it's very easy. The number of pure configurations is exactly 2 to the n over 4. Here, pure is here. Pure means or maximal independent set hits all of the edges in M star. And the main part of our proof is this. So this is the most interesting part in our proof. We show that the number of impure configurations is negligible, which means the number of maximal independent sets, which looks like this, is negligible. And once we show claim 1 and claim 2, then we are done with our main theorem. Are you okay? Are there any questions? So is it okay? I mean, okay.
Everything is okay. I can ask a question. Could you maybe explain a little bit more why do you pick every vertex from each edge? I understand that there are no edges in between because it was a maximal induced matching, but what's the intuition why the maximal independent sets are constructed this way?
Oh, okay. So that's actually that's a good question. That's the starting point of our work. So our first observation was that there is a very close relationship between maximal independent set counts and induced matching. So this is one trivial way to construct maximal independent sets. And what we observed first was this is the main method to get large number of maximal independent sets. So, and then we plan to show that the number of maximal independent sets which are not gotten by this construction is negligible. So that's what follows later. So I think I can elaborate it later. Is it okay? Okay, so this is our proof plan, and we'll talk about claim 1 and claim 2 in the following talk, but in the rest of the talk. But before we jump into the proof, let me briefly introduce the history of this problem. So as far as I know, the first result was given by Duffus, Frankl, and Rödl in 2013. They showed that log of mis QD is at most 0.78 times n over 2. And at this point, this trivial lower bound, n over 4, was already known. So there was a gap between this lower bound and this upper bound. And then in this paper, they asked, what's the truth? And this question was answered not long after. Ilinca and Kahn showed that log mis QD is asymptotic to n over 4, which was this lower bound. And in this paper, they asked, what's the actual asymptotics for mis QD, and which is now our main theorem. And here are some other asymptotic enumeration problems on QD. I think I should skip most of them, but let me tell you, as far as I know, the first work in this line was this, counting the number of antichains in Boolean algebra. This is also known as Dedekind's problem from 1890s. And this question was answered about 100 years later by Korshunov and Sapojenko. And then here are some other work, but I'm sorry, but let me skip them. And the main ingredients of our work is these 3 papers by Kahn and myself. And in the rest of the talk, I will refer to them KP1, KP2, and KP3. These are 3 different papers. So this was our proof plan. This is our first claim. Our first claim was to show that canonical matchings are indeed phases, which means typically when we choose a maximal independent set, then there is a canonical matching so that this maximal independence set either looks like this, pure, or this, impure. And claim 1 consists of 2 lemmas. The first lemma says, almost every maximal independence set is associated with some large induced matching. Let me say a little bit more. Here, large means it's close to the maximum, which is close to n/4. And here, associated needs some definition. The definition is here. Let's say M is an induced matching and I is a maximal independence set. We say I is associated with M if this I hits all of the vertices, all of the edges in the induced matching M. So you see that this definition is motivated by this picture. And so lemma 1 says, typically when we choose a maximal independence set, then there is a large induced matching so that this hits all of the edges of this large induced matching. And in lemma 2, we show that each large induced matching, so again, large means it's close to n/4. Each large induced matching is close to some canonical matching. And here, close means this. Close means, we say 2 induced matchings are close if their symmetric difference is negligible. And the combination of lemma 1 and lemma 2 gives us the claim 1, because it says, the combination of them just says that typically when we choose a maximal independence set, it hits all of the edges in a large induced matching. But lemma 2 says this large induced matching is close to a canonical matching. So eventually, typical maximal independence set hits most of the edges of a canonical matching. Okay, so once we show lemma 1 and lemma 2, then we are done with claim 1. Are you okay? Okay. So this is lemma 1. Lemma 1 says almost every maximal independence set is associated with some large induced matching. And this is the point that I said. As I said, this lemma says that there is a very close relationship between maximal independence set counts and a large induced matching. And let me give you some background. Let me start with some background. So here, let's use G for a triangle-free graph on n vertices. And Frankl and Rödl in 1993 showed that the number of maximal independent sets in a triangle-free graph G is at most 2 to the n/2. And the equality holds if and only if G is a perfect matching. So one direction of this result is trivial. If G is a perfect matching, then trivially there is exactly 2 to the n/4, 2 to the n/2 maximal independent sets, because we can choose one vertex from each edge. And Frankl says that the maximum is achieved by, this is the maximum possible number of maximal independent sets, and also this maximum is achieved by only by a perfect matching. Okay, so this is an extremal result. And once we have an extremal result, it's very natural to consider a stability version of this statement, which means this. So this is a natural question. Is it true that Miss G is close to 2 to the n/2 if and only if G is close to a perfect matching? So here, 2 to the n/2 is the maximum possible value of Miss G. And perfect matching is the unique extremal graph. So this question asks, this question is exactly a stability version of Frankl-Rödl. And to say this, we have to define what it means by G is close to a perfect matching. So for example, let's say we have this graph and this graph. Which one is closer to a perfect matching? Yeah. Of course, this question is very hard to answer, and it turned out the right definition for this question was here, this. We say that G is close to a perfect matching if the maximum size of an induced matching in G is close to n/2, the maximum value. So in this sense, this graph is closer to a perfect matching because the size in this graph, the size of the maximum induced matching is 5. And in this graph, the size of the maximum induced matching is only 3. So with this definition, one direction of this question is trivial. This direction is trivial, right? Because if G is close to a perfect matching, then that means G has a large induced matching. And we can get a large number of maximal independent sets exactly from this construction. But the other direction, this direction, is by no means trivial. And the first result was given by Rabinovich et al. In 2013. They showed that this question is, the answer to this question is yes, if G is bipartite. And later in KP1, we showed that the answer is yes for all triangle-free graphs. And so actually we showed something stronger, and our statement is roughly like this. We showed that the number of maximal independent sets not associated with a large induced matching is negligible. So this means to achieve a large number of maximal independent sets, we must have a large induced matching. So that implies this direction. Okay, so this theorem KP1 indeed says that there is a close relationship between maximal independence accounts and uninduced matching. So it seems like this theorem directly implies our lemma 1, but it's not true. Okay, so it says KP1 does not directly imply lemma 1 because of this reason. Here we say large induced matching if its size is close to the maximum, n/2. Okay. On the other hand, in lemma 1, when we say large induced matching, the size is close to n/4. Okay. So in this statement, in KP1 statement, once we have a large induced matching, then it covers most of the vertices in the graph. On the other hand, in this situation, a large induced matching covers only a half of the vertices. So this means we needed some extra argument to handle what's happening here in the other half. So we need some extra argument, but I think I should stop here for lemma 1 because we have more interesting stuff. Okay, so now let me move on to the second lemma. Are we okay with that, or do you have any quick questions? Okay. So this is lemma 2. In lemma 2, we said each large induced matching is close to some canonical matching. And as I said, this is an easy fact. An easy fact is that in QD, the Hamming cube, all of the maximum induced matchings are canonical matchings. This is what I said before, and this is easy, so let me not talk about this. And this is, again, an extremal statement. And lemma 2 is
Could you remind us what was a canonical matching?
Oh, sure, yes. So a canonical matching is a maximum size of an induced matching in the Hamming cube. And there are exactly 2 times d of them. And the construction is, first, we split the Hamming cube QD into 2 pieces of half cubes. Then there is a perfect matching between the 2 half cubes. And some of the vertices are even and some of the vertices are odd. And we choose one parity of them. Then it gives us an induced matching of size n/4. And this is the only way to get maximum size of induced matchings. So we call them canonical matchings. Okay, so one more time. Canonical matchings are the only maximum induced matchings. And lemma 2 says, lemma 2 is a stability version of that. So it says, if an induced matching is large enough, then it must be close to some canonical matching. Okay, and of course, the other direction is, again, the other direction is trivial. If an induced matching is close to some canonical matching, then it must be large. Okay, so the issue is the other direction. Can we say a large induced matching must be close to some canonical matching? Okay, so here, let me say M is an induced matching. Then, so for this lemma, a quantification is quite important because, so here large means close to n/4. And usually when we say it's close to n/4, what we imagine is the size is something like 1 minus (1) times n/4. But here, when we give this restriction, then lemma is not true. I mean, this means we need something more stronger, something stronger. So for example, lemma 2 is not true even with m as large as this much. So here you see that d to the negative 1/2 is much stronger than just saying (1). But even in this range, lemma 2 can be false. And there's some simple construction. So let's say this is the Hamming cube, QD. So in this picture, this is the 0 vector, 0 string, and this is 1 string. And what we are gonna do is to cut this Hamming cube in half. So this is the middle layer of the Hamming cube. And what we do is choose an induced matching in one direction in the upper part of the cube, and choose induced matching in the other direction in the bottom one. In this way, the size of this induced matching is more or less in this order because the size of the middle layer is n/(d). So we just exclude as many as n/(d) vertices and construct induced matchings. And this induced matching is by no means close to a canonical matching because a canonical matching is all of the edges in a canonical matching are in the same direction. Okay, so, and we conjectured that this is the only obstacle. Our conjecture is this: if the size of M is much larger than this, so this means we exclude this trivial example. If M is as large as this, then there is a canonical matching M star so that M is close to M star. So this conjecture says that this is the only obstacle, but we couldn't show this. So eventually what we showed is something weaker. We showed that this conjecture is true if we replace d to the negative 1/2 by d to the minus beta, where beta is something close to 0.58. So here, this quantity is much smaller than d to the negative 1/2. So we give a restriction that M is much larger than this quantity. So this lemma 2 is much weaker than the conjecture, but this was enough for our theorem. Okay, so this has to do with some isoperimetric property of the Hamming cube, and I will not be able to talk about the proof of this lemma, but let me briefly give you a little flavor of this part. So this is a little flavor. Let's say A is a set of vertices in QD. Then we define the edge boundary of A, or nabla of A, in this way. So this is a set of edges between A and its complement. And the vertex boundary, or partial A, is the set of vertices outside A, which is adjacent to A. So the set of these edges is nabla A, and the set of vertices is partial A. And Harper in 1960s proved this very well-known isoperimetric inequalities. So here, for simplicity, we assume the size of A is exactly a half of the Hamming cube. Harper showed that nabla of A is at least n/2, and the equality holds if and only if A is a subcube. So for example, if A is a half cube, then we know that there is a perfect matching. So in this case, the size of the edge boundary is exactly n/2. And Harper said this is the best possible for the size of the edge boundary. And he also proved that the size of the vertex boundary of A is at least some constant times n over square root of d, and the minimum is achieved if and only if A is a Hamming ball. And we've already saw an example. If A is a half ball, then the vertex boundary is just this middle layer. And I said, know that the size of this middle layer is n over square root of d. Okay, so this is the minimum possible vertex boundary of A if the cardinality of A is the half of the cube. Okay, so this is the definition of the edge boundary and the vertex boundary, but here our viewpoint is a little bit different. We see that nabla of A, the edge boundary of A, is actually the set of edges that should be removed to isolate A. So once we remove all of the edges here, then A is isolated from the other part, from the rest of the cube. And also, here, partial of A, the vertex boundary of A, is the set of vertices that should be removed to isolate A. Okay? So Harper gave the minimum possible value for the edges or for the vertices that should be removed to isolate A. Then our natural question was this: what if we are allowed to mix vertices and edges to isolate A? The picture looks like this. Here, this A is the set that we want to isolate. And to isolate A, we'll remove some vertices here. We call them W. And we'll remove some edges here. We'll call them nabla AB. And in this case, what can we say about the size of W and nabla AB? So Harper already gave, okay, let me not talk about that. So here I said it's slightly related to Margulis and Talleyrand, but I won't have time to talk about it. So let me just directly move on to our conjecture. Our conjecture says that there is a constant K such that this inequality holds. And let me make it a little bit more interesting. So here, let's take a look at this inequality. Here, if, for example, what happens if we do not have this W? That means we do not have this term here. And if there's no W, then what's nabla AB? This is simply the edge boundary of A. So in this case, this inequality is true by Harper. Okay, and now you see how the story is going. So second, what happens if there is no nabla AB? Then that means here we do not have this term. And so this means W contains the vertex boundary of A. So this inequality is true by this Harper's inequality. Okay, so this inequality is true for the two extremal cases where there is no W or there is no nabla AB. And we say that, we claim that even if we are allowed to mix vertices and edges to isolate this set A, we cannot do better. So this inequality claims that even if we are allowed to mix vertices and edges, we cannot do better. Still, the two extremal cases are the best possible. Okay, so I think this inequality is very nice if this is true, but we couldn't prove this. But the main theorem in KP2 proved something weaker. We can show that this conjecture is true if we replace this quantity, square root of d, by d to the beta, where beta is the thing like before, something close to 0.58. And the main theorem in KP2 also implies our lemma too. So everything is along in the same line. They have to do with something like isoperimetric properties of the Hamming cube. But I think I don't have time to talk more. So let me move on to the next part, the next claim. But we are done with claim 1. And are there any quick questions? Okay. So this is just to remind you where we are. So our main theorem was this QD is asymptotic to this quantity. And as I said, once we show claim 1 and claim 2, then we are done. And now claim 1 consists of lemma 1 and lemma 2, which we just discussed. So now we move on to claim 2. So it says that once we fix a phase, a canonical matching M star, then the number of, so an easy thing is the number of pure configurations is exactly 2 to the n over 4. But the most interesting part is the number of impure configurations is little o of 2 to the n over 4, which is negligible. So this is the main work in KP3. And so for the rest of the talk, I'll just briefly sketch the first part of KP3. Okay. Okay, so let me remind you, this was the picture of M star. So we decompose QD into 2 pieces of half cubes. Then we see a perfect matching, and we chose one parity. Say we chose red edges, and this is M star, a canonical matching, a maximum matching. Okay, so we fixed M star, and let's say a maximal independent set I is given. And here, this circle means this vertex is in I. And in this case, we say this vertex is occupied. Okay, so we have some occupied vertices, and it's possible that some edges is not occupied at all. And this happens if and only if this vertex, oh, sorry. If this vertex has some occupied neighbor, and if this vertex also has some occupied neighbor, then the entire edge, and then this edge is not occupied at all. However, it's not possible that both vertices are occupied because I is an independent set. Okay. So here we see a picture of a maximal independent set I. And then now what we are doing is to project this picture in this direction. Then it gives us a half cube, QD minus 1. And then we translate each occupancy in this way. If the top vertex is occupied, then we label this projection by 1. If the bottom vertex is occupied, then we label this projection by 0. If neither is occupied, then we label this projection by lambda. Okay, so in this projection, each vertex has labeled either 1, 0, or lambda. So if there are 3 labels. And finally, because this QD minus 1 is again a Hamming cube, so we just think it as this bipartition. So this is the bipartition of QD minus 1. And there are, the red vertices are even, and the odd vertices are odd, and each vertex is labeled by 1, 0, or lambda. Are you okay? So here, we haven't done anything clever. This is just, just naive translation. So we haven't done anything clever. But here, we have some conditions. There are some restrictions that this labeling must satisfy, which are here. First of all, 0 vertex cannot be adjacent to another 0 vertex because I is an independent set. So, for example, this adjacency means this vertex is adjacent to this vertex, and this is impossible because I is an independent set. And for the same reason, 1 cannot be adjacent to 1, and this is most important thing, lambda must be adjacent to both of 0 and 1 because lambda means the corresponding edge. This is not occupied at all. So that means this vertex has an occupied neighbor, this vertex has another occupied neighbor, so that means this vertex is adjacent to both of 1 and 0. Okay? So these are the restrictions that this labeling must satisfy. And then this translation gives us a bijection between the set of maximal independent sets of QD and the set of such labelings of the half cube. So from now on, instead of counting the number of maximal independent sets of QD, we can count the number of such labelings of QD minus 1. Okay. So let me give you some toy examples just to understand, just to see the calculation. So for example, what's the number of pure configurations? Here, pure means this all of the edges in M star is occupied. And that means in this picture, so this is the picture of QD minus 1. In this picture, all of the red vertices are either 1 or 0. That's what it means by this vertex or this edge is occupied. Or, yeah, this edge is occupied. And so from here, we have 2 to the n over 4 choices because we have n over 4 vertices. And once we determine all of the labels of even vertices, then there's no choice for odd vertices because of this restriction. So for example, if this vertex is adjacent to both of 1 and 0, then this must be lambda by the restriction. And if this vertex is adjacent to zeros only, then the label of this vertex must be 1. So for this reason, the number of pure configurations is exactly 2 to the n over 4. This is what I said here. So in this slide, I said it's easy to see that the number of pure configurations is exactly 2 to the n over 4. And the reason is simple because of this picture. Okay, so as I said, the most interesting part is to show that the number of impure configurations is negligible. And this is one simple example. So let's consider the case that there is exactly one impurity, which means exactly one edge in M star is missed. And here I put a question mark because actually it's impossible to have exactly one impurity, but that's just minor thing. So let's not worry about it for now. So let's pretend that we can have one impurity. So in this case, let's take a look at this picture. So here, one impurity means we have exactly one vertex which labeled by lambda, okay? And once we have, and all of the other red vertices are occupied, all of the other red vertices are either 1 or 0. And in this case, because of this restriction, lambda must be adjacent to 0 and 1, okay? Then what happens to the neighbors of this vertex? All of the neighbors must be either 0 or 1, but because this vertex is 0, so they must be 1. There's no choice for the neighbors of this vertex. And it's the same for this vertex. All of the neighbors of this vertex must be 0. There are no other choices because of this restriction. So altogether, the number of such colorings is like this. First, we have n over 4 choices for this lambda, and we have more or less the squared choices for 0 and 1 here and here. And once we have them, the number of choices for the red vertices is this much, because also this vertex has d neighbors, this vertex has d neighbors, so more or less 2D vertices lost their choices. So the number of choices for the red vertices is this much, and because n over 4 is something like 2 to the d, so when we multiply them, then we have middle of 2 to the n over 4, which says the number of such configurations is negligible. Okay, so the point of this example is this. So what's happening here is kind of like a fight between costs and savings, which means, so let me clean my picture. Which means first this is the cost for oh, sorry, this is the cost for lambda and 0, 1 vertex. So we paid something like d2 to the d for lambda and 0, 1. And by paying this, we saved as much as this. This is our savings. So we saved something like 2 to the 2d by identifying lambda and 0 and 1. And here, so our cost was 2 to the d, and our savings is 2 to the 2d. So our savings is much larger than our cost. So it gives us a desired result. Okay, so this is what's happening here. And this example shows that the real issue is actually large when we have a large set of lambdas. Because, so in this small example, we have only one lambda, so this was cheap. On the other hand, one vertex has a large neighborhood. It has as many as d neighbors. So then that gave us a large savings. However, if we have a large set of lambdas, then this set is much more expensive because we have to identify many vertices. On the other hand, as I wrote here, larger sets can have weak expansion. So that means our savings from the neighborhood is not as large as our naive example here. So we needed some extra argument to handle this situation. And this is really hard to summarize and because I don't have time. So let me just point out one ingredient. The idea was this, because the Hamming cube is a good expander. So that means usually a set has large neighborhood. So sets with small neighborhoods are rare in this situation. So that means it's very natural to expect that there must be a cheaper way to identify sets with small neighborhoods. And this idea is very natural, but the implementation is not. Our work is motivated by Sapojenko's work on Dedekind's problem and counting the number of independent sets in QD. But this implementation was very tricky, and really I cannot talk more about this. So I think this is a good point to stop. And thank you very much for listening.
Okay, I will unmute everyone for a second and let's try to give a round of applause to Jinyoung for the talk. Okay, thank you very much. Are there any questions? Everyone is unmuted now, so we might as well try to give the questions like this without writing in the chat.
Thank you. Thank you for the comment.
May I ask a question?
Go ahead.
May I ask a question?
Oh,
of course.
My question is, because when you say, I don't know if this has been studied, because when you say an independent set, if I consider Hamming cube with its graph metric, that means that every two vertices in the independent set are distance 2 or more.
yes.
So did anyone study what about a set where the distance between every two vertices is 3 or 4, or I mean at least 3 or 4 or whatever number?
Oh yeah, actually I had the same question before, and so I'm not aware of any result of that about that. And so here I mentioned Sapojenko's argument. And maybe one can try to modify this argument to answer that question. On the other hand, as I said, this method is quite tricky, so I'm not sure the answer can be directly derived from his Sapojenko's argument. So that's all that I can say.
Thank you.
Any more questions? I'll ask a question. So what do you think is a good further research line on these topics? You mentioned a couple of conjectures about D over 2, but I'm assuming that you already tried hard on those.
Yeah, so there are some conjectures on these isoperimetric inequalities, and I think it would be very nice if we can prove this conjecture, because this conjecture is just so natural. And for this asymptotic enumerations, I'm not sure. So there are some recent results which is very encouraging. So here, Jensen and Perkins revisited counting independent sets using polymer models and the cluster expansions. And also here, there is another result on independent sets in middle 2 layers. So maybe we can try the same, we can try something new in this line. I don't know, I'm not sure.
Thank you. Any more questions? Well, if not, then let's try to give another round of applause for answering all our questions and again for a great talk.
Thank you very much.
Lovely talk, Jinyoung.
Oh, thank you for coming to my talk.
Okay, everyone. See you next week, I hope.
Bye-bye.